Just wait 10 minutes, wait for Twitter to play catch up, and then we'll be off to the races. Oh, forgot to do sound check actually. Hold on, let me sound check. Yep, sound check is good. Twitter is just playing catch up still, but it'll be on soon in about 4 minutes, and we'll get cracking. Oh, and we left off with this beautiful challenge last time. C strings library, and then we got 3 more of these, and then I think what we want to try and tackle tonight is 1, 2, 3, 4. I think what we want to do is we want to try and get through enums, unions, stack and heap, and then maybe we might get through advanced pointers if we're lucky. Hopefully these are a little bit simpler. But I just saw the amount of steps here last time, and I was like, nope, I'm gonna do that another time. But we're getting close. We're getting close to the end of this. We're getting through this a little faster. There's a lot of lessons in it, so we're getting through it in a decent amount of time. Then we'll be on to a personal project after this. Should be a bunch of fun. Let's have a look what my notifications are. Just a bunch of streaks and then lost my streak and stuff like that on it. It's no prob. Level 67. Let's look at the leaderboard. Oh, I'm 4th out of 25. Top daily learners, jeez. Crikey, these guys are grinding out stuff. How do you get to an archmage anyway? Change my thing. Yeah, look at all this. It's nice. Match made. I got to reach level 100. Hope I get to level 100 by completing Boot.dev. Nah, I don't do Discord and stuff. Right, I think Twitter should be caught up now. Here we go. Yep, it's live. So let's waste no longer and get started. Okay. Make sure nothing else is going on. Nope. Right, let's get started. Okay, so we're back to C. So, C string library. So, the C standard library provides a comprehensive set of functions to manipulate strings in the string.h header file. Here are some of the most commonly used functions. Strucopy, which copies a string to another. Okay. One, two, yep, six. String cat concatenates appends one string to another. Returns the length of a string, excluding the null terminator. String length, compare. Compares two strings lexicographically. Result is negative since hello is less than world. String copy copies a specified number of characters from one string to another. Ensure null termination. String cat concatenates a specific string str and cat. Okay, it's a specified number of characters from one string to another. String stir finds the first occurrence of a character in a string. And then stir finds the occurrence of a substring in a string. Okay. Assignment: complete smart append function. It appends a source string to a destination text buffer struct. It's called a smart append because the destination buffer is a fixed 64 bytes, and in it checks for available space before appending. Appends as much as possible if there is not enough space. Always ensures the buffer remains null terminated. Returns a status indicating whether the full append was possible. So here are the steps. So if either input is null, return 1, a failure. The checks can be done with... Okay. So I've forgotten the syntax already for C. Because it's not been that long, but it's been a weekend. So hold on. If what was it? If either input, so if dest, if no dest, you can do like or, like, can't you? Like a double pipe. Oh. or not source. It's just a return, isn't it? Turn 1. Create a constant to represent the max buffer size of 64. Oh, I've forgotten constants already. I think it's just const, isn't it? Like, max buffer size of 64. Max buffer size equals 64, like that. Get the length of the string using the string length. Okay. I forgot just like basic variables. Hold on. Source length. Equals string length. Source. Calculate the remaining space in the destination buffer. Notice that it stores its own length. Don't forget to account for the null term. It doesn't count as part of the length. Calculate the remaining space in the destination buffer. Notice that it stores its own length. Don't forget to account for the null terminator. It doesn't count as part of the length. Size t remaining space equals dest. I guess it's like string length dest. It's going to be like max buffer size take, and then all that, I guess, -1, something like that. Turn 0. Print. Is it print? How do I do print? Print. Printf. Logging. And then remaining space. What's wrong with that? Called and declared library function printf. Hashtag include, what was it? This thing has to be doubles quotes. Oh, important job of the day. Important job of the day is done. Okay, right. Ugh. That wasn't incredibly helpful because it did not print out anything for me then. Whoops. Calculate the remaining space in the destination buffer. Notice that it stores its own length. Don't forget to account for the null terminator. It doesn't count as part of the length. Okay. So then, right, we do that. Pretty sure that's right anyway. So if the source string is larger than the remaining space, so if source length is greater than remaining space, then copy as much of the source string as possible into the destination buffer using the string concatenation. String concatenation. It's just remaining space, right? Copy as much of the source string into the destination buffer using this. That much. Update the destination buffer length to the max size, accounting for the null terminator. Turn 1. Destination length is equal to, don't know, max buffer. Oh. Otherwise, if there's enough space, else append the entire string to the destination buffer during string cat. Update the destination buffer length. Return 0. Nope. Then it should be 5. Um, there we go. Huzzah! Kind of shocked I actually managed to do it. Oh no. Main C29. Should return one for unsuccessful append. Hmm. What's up with this one? It's all happy and fine here. Two out of four. Main C29. Here. Submit. Test map buffer. So this is a very long string that will fill up the entire buffer. Smart append. Destination. And source. Okay. So it's 63. Max buffer size. Size remove is max buffer size. So, okay. I'm just going to ask Boots for help. Yeah, let's give him the salmon. I got a feeling it's going to be to do with this like -2 thing and stuff, you know. So very close indeed. I can see you've got the basic structure right, but there's a subtle issue in your calculation of remaining space. Looking at your failing test seems like you blah blah blah. Let me ask you why you calculate that max buffer size divided by length. Yeah, take the length. Why are you subtracting 2? Think about what you need to account for in terms of space. So the current content length, yep, and then the null terminator. How many bytes does a null terminator or actually take up? I kind of forgotten, to be honest. I thought it was two characters, wasn't it? Two. Not quite. A null terminator is just one character /0. So it only takes up 1 byte, not 2. It's just one character, but it's a slash. All right, 1. Let's try that. Yay! Okay. I'm a bit confused by that. Why is it not 2? Because there is a slash and a excellent work. You got it right. Let's all test. Don't show a question about the null terminator. While it looks like 2 characters, when you write back /0 in code, it actually isn't 1 byte in memory. The backslash is an escape character. It tells the compiler the next character's special meaning. Okay, right. That's fine. Me misinterpreting that. That's okay. Forward declaration. So sometimes you have a struct that may need to reference itself or be used recursively. For example, consider a node struct that can contain other nodes. This might be useful for building a linked list or a tree. So it contain other nodes. Blah, 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 blah. The problem here is that node T is not defined yet, so the compiler will complain. To fix this, we can add a forward declaration. The problem... Okay. Type definition structure node TT. Node. Note that the forward declaration must match the eventual definition, so you can't do something like that. Okay? Assignment. Snacklang, like Python, is built on the idea of dynamic objects. The objects need to be able to store other objects. Run the code in its current state. Notice that the .h file is producing an error because object structure references itself. Fix with the forward declaration. So we do type, whoops, where's caps lock on? Type def struct, and then what's it going to be? Snack object underscore t, like that. Okay. Mutual structs. So forward declarations can also be used when two structs reference each other, a circular reference. For example, a person has a computer and a computer has a person. Okay. Complete the complete the definition of employer. Department structs. Take a look at the implementations in the .c file to understand how they should be defined. So type def struct employee, and then type def struct department. So employee has a ID, name, and department. So char, whoops, and what was it? ID, name, and deployment. And then I guess departments score T. Well, that's why the format is not working. Hold on. It has a name and a manager. So name, which is going to be, whoops, char, name, and then what was the other thing? Manager. So it's going to be employee T star like that. Easy. Whew. Now I get to enums. So, oh, amazing. We only got four lessons in this enums one. Amazing. After all, like the slog that pointers was, then union stacks, and yeah, we go. We'll see how far we get tonight anyway. So unlike Golang, a language living in 1970, C was explicit. C has explicit support for enums, enumerations with the enum keyword. TJ is solely because Go is a simple modern language that companies actually use to ship products. Not all programming languages can be academic thought experiments like OCaml. You can define a new enum type like this. So type definition enum days of week T. Okay, the type def and its alias days of the week T are optional. But like with structs, they make the enum easy to use. In the example above, days of week T is a new type that can only have one of the values defined in the enum. So Monday, which is 0, Taco Tuesday, which is 1, Wednesday is 2, Thursday is 3, Friday is 4, Saturday is 5, and Fun Day is 6. You can use the enum type like this. So yeah, or if you don't want to use that, use the alias type struct event. Oh, days of week T, okay, day. If you don't want to use the alias, enum days of week, okay. An enum is not a collection of type like struct, or an enum is not a collection type like a struct or an array. It is a list of integers constrained to a new type, where each is given an explicit name. Assignment. The Snackland graphics library needs to represent colors. Create a color enum and the color T type definition with red, green, and blue values in that order. So I'm going to try and remember off the top of my head now. So it's going to be type def enum, and then color, and then it's going to be red, green, and then blue. Why is indentation this like work terribly? Like that. Type def enum, color, and then that at the end. Let's do it straight away because I'm confident. Yay! Starting to remember syntax a little bit now. It's good. Non-default values. So sometimes you don't just want to enumerate some names where the underlying integer constant values don't really matter. You want to set those enumerations to specific values. For example, you might want to define a program's exit status codes. Okay, yeah. Alternatively, you can define the first value and let the compiler fill in the rest, incrementing by 1. So type definition enum, exit success, exit failure, exit command not found, exit status enum, words per minute, lane words per minute, prime words per minute, and TJ words per minute. Assignment, update the color enum with the following values. So red is 55, green is 176, and blue is 38. Command Shift Enter, pretty confident. Huzzah. This is the nicest, easiest lesson I've had yet. No hassle whatsoever. Switch case. One of the best features of enums is that they can be used in switch statements. Enums plus switch statements. Avoid using magic numbers. Use descriptive names. With modern tooling will give you an error / warning that you haven't added all the cases in your switch. So here's an example. So switch on log level, case log debug. log info, log warning, log error, and all that nice stuff. You'll notice that we have a break after each case. If you do not have a break or return, the next case will still execute, falls through to the next case. Many devs have written bugs when using switch statements because they forgot to add a break. In some rare cases, you might want the fall through. So, for example, here's 1, 2, and 3 are all minor errors. Break, 4 and 5, and then default. You do that. But usually it's a foot gun. You almost always want a break at the end of each case statement. So assignment, complete the HTTP to str function given the enum defined in http.h. It should return a hard-coded string with the human readable version of the HTTP stays code. Okay. Code C. Okay. Okay, so switch code this, then case and the syntax is, so we just do case that and then return uh, 400 bad request. One, two, three, four, five. Four, four not found. 418, I am a teapot. I am a teapot. 500 internal server error. Internal server error. Easy pleasy. Last one in enum. So size of enum, the same size of operator can that we talked about works on enums. Generally, enums in C are the same size as an int. However, if an enum value exceeds the range of an int, the C compiler will use a larger integer type to accommodate the value, such as an unsigned int or a long. Unsigned int doesn't represent negative numbers, so it can represent larger positive numbers. Long is just a large integer type that longer integer type than int, so it can represent larger numbers. We use the C compiler will use the larger integer type to accommodate the value, such as an unsigned int or a long. Okay, long is just larger int. Unsigned int doesn't represent negative numbers, so it can represent larger positive numbers. Just fancy integers. So enums are often just used to represent possibilities in a set. For example, small, medium, large, extra large. Your code probably cares a lot about which size a variable represents, but probably doesn't care that small happens to be 0 under the hood. From the compiler's perspective, enums are just fancy integers. Assignment. At the start of main, print the size of the two enums defined in main C in the format. Remember to use the format for size of T, okay? So I guess print F like this. /n like that, and the size of the big numbers is y, so it's going to be zu, so zu. That's going to be can't remember how I use the size of, is it a function? Yeah. So the size of that. Whoops. And size of whoops. Semicolons. Boom, just like that, we're on chapter 5. So we might get to chapter 7 tonight. Let's see how unions has not got a lot of things in here, and I think maybe stack and heap probably going to have a fair bit in them, so we'll see how it pans out. Now that we understand struct and enums, we can learn about unions, a combination of two concepts. This is not the kind of union that 300k earning employees fight for because they are underpaid and don't have enough oat milk in the office kitchen. No, this feature is one that even Golang doesn't have, probably because they were worried about getting fired from Google for just mentioning the word. Unions in C can hold one of several types. They're like a less strict sum type. So they're like a less strict sum type. From the world of functional programming, here's an example of a union. They're a less strict sum type. Okay, so type def union, age or name. So int age, character name, blah blah. The age or name T type can hold either an int or a character, but not both at the same time. That would be a struct. We provide the list of possible types so that the C compiler knows the maximal potential memory requirement and it can account for that. This is how the union is used. So age age or name T, lane equals age equals 29. Print the age of lane. Here's where it's getting interesting. What happens if we try to access the name field even though we set the age field? We get nothing. To be more specific, we get undefined behavior. A union only reserves enough space to hold the largest type in the union, and then all the fields use the same memory. So when we get .age to 29, we are writing the integer representation of 29 to the memory of the lane union. Then if we try to access .name, we read from the same block of memory but try to interpret the bytes as a character, which is why we get garbage, which is interpreted as nothing in this case. Put simply, setting the value of .age overrides the value of .name and vice versa, and you can only access the field that you set. Assignment. Snetclang is going to need objects. We'll hand code those objects, and Snetclang developers will use them to store dynamic variables, kind of like Python. Everything is an object, even simple integers and strings. Take a look at the Snec object struct in exercise.h. It has a kind of field that stores the type of the object, like integer or string, and a data field that stores the actual data. Create a Snec object kind enum type in the exercise.h. It's the one uses. So type def enum. Create a Snec object kind enum type in exercise. It's the one used as the kind field of the provided Snec object. Of the provided Snec object. It's an enum that can be an integer 0 or a string 1. Okay. So Snec object kind. That's going to be integer or string. Like that. Complete the format object function in exercise C that uses a switch on the kind of the Snec object T and writes a formatted string to the associated buffer. So switch on the object, and I guess case integer and we just do a break just to, and then case string was the other one, was it? Case string break. So it says for an integer write int into the buffer, int colon n into the buffer to replace n with the integer value. Sprint f. So buffer, buffer is where it's going. Hold on. Point to a buffer in the format. And then int colon that's going to be %n like that. It's going to be objects. With the integer value. Whoops. That kind. This will be data, right? Okay. Whoops. Semicolons. Object data. Not a pointer, is it? So I don't have to do that. Print, whoops, print string. Pretty confident in that. Switches on the snapped object kind like that. For an integer, write into the buffer, replacing n with the integer value. For a string, do the same. Guess what we could do is just undo that and just see what that does. Alignment fail. Not sure what's wrong here, Boots. What's wrong with this, Boots? Skim the fish. I feel like it's simple. Look closely at your sprint F formatting issue like that, yeah? Using n as the format F specifier, but n is a very special and dangerous formatting specifier. It doesn't print a number. Instead, it writes a number of characters. What format is you supposed to print into? I thought it was %n. Is it not? Oh, D. Oh, I don't know why I got confused with that. Digit. Now will it run? Ugh. Don't lose salmon just for silly stuff like that, my friend. Digits. Okay, and string. Read closely. Union. So memory layout. So unions store their value in the same memory location, no matter which field or type is actively being used. That means that accessing any field apart from the one you set is generally a bad idea. Accessing any field apart from the one you set is generally a bad idea. Assignment. Take a look at the value or error T union. It represents either an integer or an unsigned non-negative integer error code. Run the code in its current state. Notice that the dot value field is set to minus 420. Then the data in each field is printed. The dot value field works as you expected, printing minus 420. However, the dot error field prints 40 blah 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 blah. It's trying to interpret the bytes of minus 420 as an unsigned integer, which results in a very large number. Uncomment the next block of code and run it without submitting. Whoops. Notice how that we set the dot error field an unsigned integer. To unit max, which is a constant representing the largest unsigned integer. In my case, as expected, the dot error field prints that. However, the dot value field prints minus 1. It's interpreting the bytes that represent that as an unsigned as an unsigned integer and assigned integer -1. Submit the fully uncommented code. Yeah, okay. Union size. So a downside of unions is that the size of the union is the size of the largest field in the union. Take this for example. So int or error message. So data is an int or error message is a character. It's 256 bytes. This int or error message union is designed to hold an int 99% of the time. However, when the program encounters an error, instead of storing an integer here, it will store an error message. The trouble is that it's incredibly inefficient because it allocates 256 bytes for every int that it stores. Imagine an array of 1,000 int or error message t objects. Even if none of them make use of the .error field, the array would take up 256 times 1,000, which is 256,000 bytes in memory. An array of ints would only take up 4,000 bytes, assuming 32-bit integers. So quiz examples. Assume the following. Size of an int is 4, size of a character is 1, and size of a long int is 8. So union there. So how many bytes will the instance of sensor data require? 8. Which is the correct order from least to greatest of the memory requirements of the given unions? So which has the most? An int is just 1, right? Oh, wait, no. An int is 4. So no matter what this is going to be a 4. And this is going to be big in some way. So least to greatest. So it's going to be sensor data. It's going to be item, sensor data, then packet thing. Item. Oh, wait. Item, sensor data. Oh. Actually, hold on. Struct. Hold on. For 8, 12. So 12. It's going to be 8, 12 in that one. So sensor data, item, that one. Last one, so helper fields. One interesting, albeit not commonly used trick is to use unions to create helpers for accessing different parts of a piece of memory. Consider the following. So direct definition, union of color. So it has a struct of uint8 type for RGBA, which is components, or just RGBA. It results in a memory layout like this. So RGBA is unit 1 byte each. Okay. Only 4 bytes are used, and unlike in 99% of scenarios, it makes sense to both set and get values from this union through both the components and RGBA fields. Both fields in the union are exactly 32 bits in size, which means we can safely access the entire set of colors through .rgba field, or get a single color component through .components field. The convenience of additional fields with the efficiency of single memory location and the fragility of C. So complete the packet header. Snacklang has support for networking, so complete the packet header union. It should have 2 potential fields. So TCP header, which is struct. So it's going to be struct like that. It's going to be called TCP underscore header. And it's going to have the first 2 bytes are the source port. Use the unit int 8 for the types of the fields based on the number of bytes needed. Remember, 8 bits is 1 byte. So that's 1 byte, 2 byte, 4 byte. Forgotten how to do an array. Whoops. First 2 bytes. Source port. Destination port. Whoops, forgot how to do arrays. Uh, yeah, that's not right. I'm not quite sure how to do the an array. How do I do that? Like that. Ooh, like that. Oh no. 2 bytes, 4 bytes, right? 64. Hmm. Something slightly. Whoops. Slightly off here. Just give him the fish. Yeah, pointer itself is only 4 bytes in your system or 8 bytes and blah blah blah, but you actually need is an array of 8 bytes. Looking at the test failing, checking the raw field, blah blah blah. How can you change the declaration raw to make it an array of 8? Oh, hold on. Is it like this? Like that? No. How do you do it like an array? Like that? I don't know. Oh, right, okay. Right, this is syntax I've not remembered very well. Okay. Yeah, arrays are confusing for me still in C. Okay. Right. I think we can get through stack and heap tonight. We can have a look at advanced pointers. Whew. Maybe another night. Let's see. Gotta get through the stack first. We've got 8 lessons to get through here before we can reach the end. But we're doing all right. How you doing out there, peeps? You having fun so far? You learning anything along the way? Having a laugh at how bad my C knowledge is because I've never written it before. It's all good. We start somewhere. So, okay. I think let's at least finish stack and heap tonight, and then we'll see about this one, because then the next 4 lessons should be a let's wrap it up type of thing. So stack. So remember how I told you that memory is basically just a giant array of bytes with addresses at various offsets? That's true, but it also has some additional structure. In particular, memory is divided into 2 main regions, the stack and the heap. We'll cover the heap later. The stack is where local variables are stored. When a function is called, a new stack frame is created in memory to store the function's parameters and local variables. When the function returns, its entire stack frame is deallocated. The stack is aptly named. It is a stack or last in, first out data structure of memory frames. Each time a function is called, a new frame is pushed onto the stack. When the function returns, its frame is popped off the stack. Take a look at this example function. So void create typist uses nvim, words per minute 150, character name 4 TEGJ even. Say we create typist 1. Before the call, our stack memory might look something like this, with the next memory address to be used. 0x0004. Once called, the stack pointer is moved to make room for the return address to pick up the execution after the function returns. Arguments to the function. Once the stack pointer is moved to once called, the stack pointer is moved to make room for the return address to pick up execution after the function returns. Arguments to the function, local variables in the function body. So return address, stack pointer, stack frame. And the local variables are stored in the stack frame. So from here to here. When the function returns, the stack frame is deallocated by resetting the stack pointer to where the frame began. Run the code. Run the code in its current state. See how each successive nested call, print message 1, see how each successive nested call, print message 1 calls print message 2, calls print message 3. The memory addresses the memory addresses allocate more and more space. More like message. Okay. The memory addresses allocate more and more space. Update where print message 2 and print message 3 are called from, so that all of the functions use the same stack space. The offsets printed by print stack pointer diff should now be different from before. The print stack pointer diff calls should remain at the start of each function. Stack pointer offset, okay. How do I... So update print message 2 and print message 3 are called from so that all three functions use the same stack space. How do I do that? The print message functions should not call each other because that creates a new stack frame on top of each one. They should all sequentially. All right, okay, it's just saying lift them up and put them in the same function. Yeah, can you explain this, Boots? Just like move it into the same thing. Is that just why? So. Oh, you could have left them as is. Right, okay. But just, oh, where they're called from. Right, I see. Right, okay, I got the same result but in a completely different way. Right, because when it's in here and then we call print message 2 in the previous one. Right, okay. Yeah. Could do with explaining that actually. Can you explain why calling in the same function makes a difference? Just so I got a grasp of it. Truly accepts question. You hear concepts of functions and memory work together. The main difference lies in how we call the stack behaves. Let's break it down. When you add the original code where print message 1 called print message 2 called and print message 2 called print message 3, here's what happens in the stack. So main calls print message 1. A new stack frame is created for print message 1 on top of main stack frame. Inside, creates a new stack frame and a new. Okay, each time a new function is called, a new stack frame is pushed onto the stack. And this takes up more memory space. Yeah, it's showing the difference between the stack's points position. If these new frames were added, you would see a non-zero effect reflecting the size of blah blah blah. Now your current code calls happening the same print message function. Yeah, also operations, printing messages and calling happen inside that same stack frame. Yep, okay. So why is stack? So allocating memory on a stack is preferred when possible because the stack is faster and simpler than the heap, which we'll get to. Be patient. Efficient pointer management. Stack allocation is just a quick increment or a decrement of the stack pointer, which is extremely fast. Heap allocations require more complex bookkeeping. Cache-friendly memory access. So stack memory is stored in a contiguous block, enhancing cache performance due to the spatial locality. Related values live next to each other in memory. The CPU can load and access them more quickly. Automatic memory management. Stack memory is managed automatically as functions are called as they return. I don't think it meant to have that and there. Inherent thread safety. So each thread has its own stack. Heap allocations require synchronization mechanisms when used concurrently, potentially introducing overhead. One reason Go programs are efficient is that Go uses stack allocation for variables when possible, much like C. The Go compiler performs escape analysis to decide whether a variable can be allocated on the stack. On the other hand, languages like Python allocate most objects on the heap, which can impact performance. So generally speaking, it's more performant to store variables on a video cassette, ticker tape, stack, or the heap. Stack. So the famous Stack Overflow that I've never really understood, which I will now. Stack Overflow. So the stack is great and all, but one of the downsides is that it has a limited size. If you keep pushing frames onto the stack without popping them off, you'll eventually run out of memory and get a stack overflow. Yes, that's what the famous site is named after. So if you keep pushing frames onto the stack without popping them off, you eventually run out of memory and get stack overflow. That's the one reasons recursion without tail call optimization can be dangerous. Each recursive call pushes a new frame onto the stack, and if you have too many recursive calls, you'll run out of stack space. Assignment. Snetclang is admittedly a fairly inefficient language. Don't tell the VC investors. Sometimes, rather than carefully managing memory, the Snetclang interpreter allocates a big chunk of stack data, simply because the creators, us, are too lazy to allocate the right amount. Anyhow, the BDFL, the what? BDFL, benevolent dictator for life. The Snetclang has allowed this laziness, but only to a maximum amount of 10 kilobyte. A kibibyte, amount of 10 kibibyte. A single kibibyte is 1024 bytes. Run the code in its current state, you should get back a stack overflow, which will calls a segmentation failure. Segmentation fault. Okay. Fix the pool size so that it allocates exactly 10 kibibyte. Yay. So pointers to the stack. So we know that stack frames are always getting pushed and popped, and as a result, memory addresses on the stack are always changing and getting reused. Remember, the stack is only safe to use when within the context of the current function. Assignment. Let's get back to Snetclang's built-in 2D graphics library. Take a look at the new quad function. It accepts an x and y value and creates a new pointer to a stack allocated quad t struct. Run the code in its current state. You should see something weird. Why don't the x and y values match the ones passed in on lines 16 and 18? They're all 50, 60, 50, 60, 50, 60. Because we're accessing stack memory, the pointer created on line 12. Okay. Outside the function that, because we're accessing stack memory, the pointer created on line 12, outside the function that created it, the memory has been deallocated and is no longer safe to use. Technically, the behavior is undefined, but it's likely that in this specific scenario, we're just seeing it get overwritten by the next function call versus 50 and 60 always prints. Fix the new quad function so that it returns a struct, not a pointer to a struct. This will force the compiler to copy the struct to the main function stack frame. So I guess it's just that, right? And oops. This will force the compiler to copy the struct to the main function stack frame, and the memory will be safe to use. You'll have to update syntax in a few places to accommodate the change. No. So needs to be dot. There we go. The heap. Okay, let's have a listen.
The stack and the heap aren't just abstract concepts that are applicable when writing low-level C code. In fact, they are useful even if you're having a bad day and being forced to write TypeScript. The stack and the heap are two different regions of memory. The stack is simpler and faster, but it is a bit more limited. And the heap is slower and a bit more complex to work with, particularly in languages where we manage our own memory, but it does allow us to create more sophisticated and complicated data structures. Let's first start with talking about the stack. An important thing to remember as we work through this in C is that C always needs to know how large some piece of data is and where to put that data. So when we look at a function like this, for example, create typist, we have some input variables, which we usually call arguments. For example, uses envim. We also have the words per minute and a character array for a name. C needs to know where to put all of these so that it can access them later. Remember, everything in C is about having some sort of name, an address, and then a value. The C compiler knows how large each of the different data types are, does not need to dynamically allocate any of them. So they'll all be placed on the stack. And in this case, and roughly in C, you can think about getting a new stack frame every time you call a function. So when we call create typist, we're going to create a new stack frame. This means we're going to have a return address and the new stack pointer. The return address tells us where we're going to go once we're done with this function. So after everything's completed executed, we'll move the stack pointer back to this spot in memory. The stack pointer tells C where we currently are in case we have another function call and we need to create a new stack frame. The first thing that's going to be put into the stack frame are any arguments to the function. In this case, we just have one argument, uses envim, and so that will be copied into this stack frame. Very important when we're thinking about function arguments to remember that they're getting copied. The second thing that's going to be put into the stack frame is the int that is inside of that function scope, which is words per minute. And then lastly, we have to reserve space for each of the characters of the array, and so we have the TEEJ characters stored in that stack. Once this function returns, then we will move the stack pointer back to the return address, effectively freeing all of that memory to be used again later if we have another function call. Now compare this with the heap. Instead of being this static array of memory that we sort of push and pop off the top of, the heap is much slower because we need to dynamically allocate this memory and grab new resources from the operating system, as well as a bit more complex because it is possible to forget to free that memory, at least in languages like C, which would lead us to memory leaks and possibly running out of memory completely on the computer. Wondering, why would we ever want to use the heap? It's slower, more complicated, and can lead to memory leaks. We are going to use the heap because sometimes we don't know the size ahead of time of the different objects that we're going to use. Now, consider the scenario where you have a list of users. For a lot of you, you may know ahead of time that that list will always be empty. But for some cool people like Lane, I will admit he does have a few users. They may have to dynamically allocate something like all of the users who haven't logged in the last 3 months. Because we don't know that number ahead of time, we may need to dynamically allocate and continue to expand a region to store those users' data as we get more and more users to put in the list. So generally speaking, what you should be thinking is the stack is for things that we can know ahead of time and that only need to exist within one function. And the heap are for things either that we don't know the size ahead of time or that we need to return back outside of the function that may have some allocations.
Okay, so the heap is the opposite to the stack. It's a pool of long-lived memory shared across the entire program. Stack memory is automatically allocated and deallocated as functions are called and returned, but heap memory is allocated and deallocated as needed, independent of the burdensome shackles of function calls. When you need to store data that outlives the function that created it, you'll send it to the heap. The heap is called dynamic memory because it's allocated and deallocated as needed. Take a look at new int array. Oh, memory allocation. Okay. Okay, because the size of an array isn't known at compile time, we can't put it on the stack. Instead, we allocate memory on the heap instead. Heap using the standard library's header malloc function. It takes a number of bytes to allocate as an argument size times the size of int, and returns a pointer to the allocated memory, a void array that we cast to an array of ints. So here's the diagram of what happened in the memory. So the heap just big heap of just big space. The new int array function's size argument is just an integer. Yep. It's pushed onto the stack. Assuming the size is 6. Then malloc is called. We're given enough memory to store 6 integers on the heap, and we're given the address of the start of the new memory allocated. We store it in a new local variable called new array. The address is stored on the stack, but the data it points to is in the heap. Let's look at some code that uses new int array. So new int array 6, an array of 6. So array of 6, 0, 1, 2, 3, 4, 5 is like that. So the data is stored in the heap. When we're done with the memory, we need to manually deallocate it using standard library H's free function. So free array of 6, that. The free function returns, deallocates that memory for use elsewhere. It's important to note that the pointer array of 6 still exists but shouldn't be used. It's a dangling pointer pointing to deallocated memory. Assignment. Run the getFullGreeting function in its current state. If you take a look at the main.c file, you'll notice that it's testing to ensure that a pointer to stack memory isn't returned, which you never should do because it's undefined behavior. So if you look at main C. Okay. Fix the getFullGreeting function so that it allocates memory on the heap and returns a pointer to that memory. Use the provided size parameter to allocate enough space for the resulting string. Be sure to account for the size of each character. Function allocates to the heap and returns a pointer to that memory. Use the size parameter to allocate enough space for the resulting string. Be sure to account for the size of each character. Ugh, not gonna lie, my brain's starting to we're at now. That it allocates memory on the heap and returns a pointer to that memory. Use the size provided prior to allocate enough space for this resulting string. Be sure to account for the size of each character. Should truncate to fit buffer. There we go. Let's have a look at solutions, see if there was something a little nicer. Yeah. Oh, they just use size. They even need to do that. But they did the same thing. Okay. Kind of understand it. I'm not like, yeah. Oh gosh. Yeah, I think we're only doing this lesson tonight because yeah. So malloc. So the malloc function, memory allocation, is a standard library function in C that allocates a specified number of bytes of memory on the heap and returns a pointer to the allocated memory. This new memory is uninitialized, which means it contains whatever data was previously at that location, if the programmer's responsibility to ensure that the allocated memory is properly initialized and eventually freed using the free to avoid memory leaks. If you want to make sure that the memory is properly initialized, you can use the calloc function, which allocates the specified number of bytes of memory on the heap and returns a pointer to the allocated memory. The memory is initialized to 0, meaning it contains all zeros. So function structure, so void malloc, blah blah blah. Size is the number of bytes to allocate and return a pointer to the allocated memory, or null if the allocation fails. Example, allocates memory for an array of 4 integers. So pointer int or 4 times and if it's null, handle memory allocation failure, printf, return exit, and use the memory here, free here. Manual memory management. So the idea of manually calling malloc and free is what puts the manual in manually managing memory. The programmer must remember to eventually free the allocated memory using the free pointer to avoid memory leaks. Otherwise, that allocated memory is never returned to the operating system for use by other programs until the program exits, at which point the operating system will clean up after it. But that's not ideal. Manually managing memory can be error-prone and tedious, but languages that automatically manage memory, like Python, Java, and C#, have their own trade-offs, usually in terms of performance. So assignment, we're working on some of the dynamic memory management tooling that we'll eventually need to build a garbage collector for Sneklang. So complete the allocate scalar array function. It should accept size and multiplier parameters and should allocate an array of size integers on the heap. Allocate an array of size integers on a heap. Okay. Gracefully return null if the allocation fails. So if initialize each element in the array to the index times the multiplier. So e.g. a multiplier of 2 would result in return a pointer to the allocated memory. So return size whoops. Initialize each element in the array. Okay. Here. How do I do for loop again? Whoops. So for, hold on, let me figure this out. So for, and it's going to be, I equals 0. Is it semicolon or is it like that? And then it's going to be the comparison thing. So while I is less than size, I guess. Size, and then I plus plus. So is it like that? Forgot the int part, so int. It's a semicolon, okay. Then I guess size, I equals I times by the multiplier. Does that work? Okay, let's not call it that. It was confusing. Parameters and should allocate an array of size integers to the heap. Hmm. Maybe if I just remove that, does that solve the problem? Nope. Hmm. Well, my game, I don't want to be on here forever, so like, what's wrong with the first part? Nah. Problem is how you're handling case when malloc fails. When malloc returns null indicating you're calling exit one, which immediately terminates the entire program. However, the assignment asks you to gracefully return null if the allocation fails. What do you think you should do instead of exit one? Oh. Can't I just turn null? Oh, that way. What do you think happens when you use address of operating? So I would return instead. Look at your final test space. You're returning with already pointed to allocate memory. Okay. Yay! Just some tactical stuff. Okay, so last two for tonight, because brain's getting a little bit smoky. Might be that this we end up sort of not completing this week, but I'm not going to have time to do advanced points tonight. So the free function deallocates memory that was previously allocated by malloc, calloc, or real lock. Important, free does not change the value stored in the memory, and it doesn't even change the address stored in the pointer. Instead, it simply informs the operating system that the memory can be used again. Forgetting to call free leads to a memory leak. This means that the allocated memory remains occupied and cannot be reused. Even though the program no longer needs it, over time, if a program continues to allocate memory without freeing it, the program may run out of memory and crash. Memory leaks are one of the most common bugs in C programs, and they can be difficult to track down because the memory is still allocated and accessible even though it's no longer needed. Assignment: we may be inefficient here at Snecklang, but we don't want outright memory leaks. Run the code in its current state. After a number of successful allocations, you should get a failure. The program is running out of memory due to a leak. See how it's calling allocate scalar list function in a loop? Well, the lists aren't needed from loop to loop, so they should be freed at the end of each iteration. If we do that, we should be able to allocate as many lists as we want, because we return the memory in between iterations. Fix the code by freeing the allocated list at the end of each loop. So list, so then we can do free lst. Whoops, semicolon. Huzzah. That was easy peasy. Big endian and little endian. So while we are on the topic of memory, it's worth knowing about endianness. Endianness is the order in which bytes are stored in memory. The two most common formats are big endian and little endian. So big endian. In a big endian system, the most significant byte is stored first at the lowest memory address. The most significant byte is just a fancy way of saying the biggest part of the number. Let's say you have the hexadecimal number 0 times 1, 2, 3, 4, 5, 6, 7, 8. Here's how it would be stored in big endian format. So lower addresses, most significant, least significant high addresses. So 0x12, 0x34, 0x56, 0x78. Alright, okay. And the most significant byte is 0x12. Is stored in the lowest memory address. Big endian system. In big endian system, the most significant byte is stored first, the lowest memory address. Most significant byte is just a fancy way of saying the biggest part of the number. Let's say you have little endian. The most significant byte is 0x12 is stored at the lowest memory address. Little endian. So in a little endian system, the least significant byte, the smallest part of the number, is stored first at the lowest memory address. This is a format used by most modern computers. Use this same number that. Here's how it would be stored in little endian format. So most significant to the least. Here, the least significant byte is 0x78. Is stored first. For the most part, you don't have to worry about endianness when writing programs. The way data is read from memory automatically handles this, so we can spend our valuable time building e-commerce shops for the terminal instead. Endianness becomes important in certain scenarios like networking and working with binary files. For now, just know that modern systems use little endian, and the compiler takes care of how data is stored and accessed. In little endian system, how would the hexadecimal number that be stored in memory? Little endian, so that way around. C3, yep, so you basically flip it, and yeah, put the end that way first. Okay. Yikes. Pointers, array pointers, void pointers, swapping inches. Oh, do I want to get into this now? Yeah, I'm thinking maybe not. We have got an hour, but array of pointers. Nope. We'll get onto this tomorrow. That's going to be it for tonight. Well, hope you've had fun. I have and haven't at the same time. It's been a bit of a stressful one, but we're getting there. We're almost through the memory management course, and this has been definitely a tough one. This is way out of my field. But tomorrow night, if we at least get through, I guess the next 3 sort of modules or more, depending on how much is in each one. Just kind of a little peeky look at some of these. Some of them are a bit longer, yeah, so it might be that we end up taking, oh yeah, some of them look long, so maybe it's going to stretch into next week, I think, but it is what it is. So yeah, for tonight, thanks for coming down. Hope you had fun and learned something. If you have, yeah, just leave it a like, follow, message, wherever you fancy. Thanks for coming down, and see you next time.